Hello friends, myself Anjali Shinde from Department of Mathematics, S.V.K.T. Devali Camp College, Nasik. Today we are going to see calculus part F5 BSc and we are going to see ordinary differential equations. You know that what is a differential equation, what is order and degree of the differential equation. Today we are mostly going to concentrate on linear first order differential equation. So what is meant by linear equation? A linear first order differential equation has always of the form dy by dx plus pxy is equal to fx, or we can say y dash plus pxy equal to fx. So this is known as linear first order differential equation. A equation which cannot be written in this form is said to be non-linear. This equation is said to be homogeneous equation if fx equal to 0. That is, a equation of the form y dash plus pxy equal to 0 is known as linear first order homogeneous differential equation. If fx is not equal to 0, then that equation is known as non-homogeneous differential equation. Now in this equation, if we consider y equal to 0, then this obviously satisfies this homogeneous equation. So y equal to 0 is always solution of the equation y dash plus pxy equal to 0. Such a solution is known as trivial solution of this homogeneous differential equation. Any other solution than this solution is known as non-trivial solution. Now what are examples of this linear differential equation? So consider some examples. For example, y dash is equal to 1 upon x square. This is linear differential equation of first order, or you can say y dash plus 3y equal to sin x. This is also linear differential equation. Consider this equation. Observe that this equation is not directly in the form y dash plus pxy is equal to fx, but it can be rewritten in this form by dividing by x. So y dash plus 3xy upon x, that is 3y is equal to x square upon x is x. So observe that though this equation originally is not in this form, it can be rewritten as y dash plus 3y is equal to x, now which is in this form. So this equation is also a linear equation. So linear equation is always of this form. So what are non-linear equations? The non-linear equations are, for example, if I consider xy dash plus 3y square is equal to cos x. Now observe that instead of y, here it is y square. So obviously this is non-linear because of y square term. So this y square term makes this differential equation to be non-linear. Or if I consider 3y dash equal to sin x. Observe this product term y dash. Because of this product term y dash, this equation becomes non-linear. Or you can say y dash plus x log y equal to 0. See, this equation, because of the term log y, it becomes non-linear due to log y term. Or even you consider y dash plus x e raised to y is equal to cos x. This is also non-linear due to e raised to y term. So we know what is meant by linear and non-linear differential equation. Now we are going to see what is meant by general solution of this linear differential equation. So if we have the linear equation, that is y dash plus pxy is equal to fx, then there is a unique formula y is equal to y of xc, where c is a constant. We know it is arbitrary constant, and it is such that for a fixed value of c, a formula in terms of x is a solution of this equation y dash plus pxy is equal to fx, and if y is the solution of this equation, then y can be obtained from this formula using some specific value of c. That is known as general solution of this equation. For example, if you consider y dash is equal to 1 upon x square, then for this linear first order differential equation, we have the solution as y is equal to minus 1 upon x plus c, where c is arbitrary constant. So this is known as general solution of this differential equation. Why this is solution? Because if you differentiate it, we get that this equation is satisfied. See, differentiating y, we get y dash is equal to differentiation of this is 1 upon x square. So differentiating y, we get y dash is equal to 1 upon x square, which is our original differential equation. So this is known as solution, and this solution is known as general solution of the differential equation. Sometimes some initial values are given to us. That is, initially when we get x and corresponding value of y, we are able to find the value of this arbitrary constant, and then we get the solution, which is particular solution. So we want to study what is general solution of homogeneous differential equation. So firstly, we want to find the general solution of linear first order differential equation, which is homogeneous. That is, we want to find the solution of y dash plus pxy equal to 0. This is homogeneous differential equation. It is linear and first order. One of the methods to find the solution of this general equation is nothing but separation of variables method. What is this separation of variables method? As the name suggests, the variables are separated. Means that all y terms are on one side and all x terms are taken on another side, and then we get a variable separable form. Variable separable form means the variables are separated. So all y terms on one side and all x terms on other side, that is variable separable form. And integrating this variable separable form, we get the general solution. For example, suppose we have the equation y dash plus x upon 2 y equal to 0. Now observe that dy by dx plus x by 2y equal to 0. So I am able to write down this as dy upon dx is equal to minus x upon 2y, or we are able to write down dy upon y is equal to minus x upon 2 dx. See that LHS is totally in terms of y and RHS is totally in terms of x. So this is known as variable separable form. Y on one side and total x terms on another side. So this is variable separable form. Integrating this variable separable form, we get the solution of this homogeneous differential equation, and therefore this method is known as separation of variables method. Note that every equation cannot be written in variable separable form. For example, if we have the equation dy by dx is equal to x plus y bracket square, then this equation we are not able to directly write as variable separable form. That is, we are not able to separate y terms and not able to separate all x terms, and therefore this is not directly variable separable form. So today we are going to see mainly those homogeneous differential equation which are linear first order and which can be written in this variable separable form, and that method is known as separation of variables. So the name itself suggests what is the method. We have to separate the variables y on one side and x on another side. That form is variable separable form, and integrating that we get the general solution of this equation. So consider some examples to get the idea. For example, find the general solution of y dash minus ay equal to 0, and hence find or hence solve the initial value problem y of x0 equal to y0, where a is given to be constant. So observe that this is homogeneous differential equation. So see, the given equation is nothing but y dash minus ay equal to 0. This is our given homogeneous differential equation. That is dy by dx minus ay equal to 0, or we say dy by dx is equal to ay. We want to write down the variable separable form. So what is variable separable form? Dy upon y is equal to a dx. This is nothing but variable separable form. And once we get variable separable form, we integrate this equation. So integrating, we get integral dy upon y is equal to integral a dx. That is, ln of mod y is equal to ax plus k, where k is constant of integration. Therefore, mod y is equal to e raised to ax plus k, or mod y is equal to e raised to ax into e raised to k. Or we can say mod y is equal to c e raised to ax. Or we can say y is equal to simply y is equal to c e raised to x, where c is nothing but e raised to k if y is greater than 0, and it is equal to minus e raised to k if y is less than 0. That is, c is a constant. So observe that y is equal to c e raised to ax, where c is the constant, is known as general solution of this differential equation. Now, if you want to find the initial value problem, solve the initial value problem, we have to put x is equal to x0 and y is equal to y0 in this solution. So, if you put x is equal to x0, so our solution is now y is equal to c e raised to ax. If you put initially x is equal to x0, then we have y is equal to y0. So, substituting in this equation, we get y0 is equal to c e raised to ax0. From this, we get the value of c, that is c is nothing but y0 e raised to minus ax0. We divide by e raised to ax0. So, on this side, this e raised to ax0 becomes e raised to minus ax0. So, this is value of c. So, we find the value of arbitrary constant c and put that value in equation 1. So, solution becomes y is equal to y0 e raised to minus ax0 into e raised to ax. It is nothing but y0 e raised to a into bracket x minus x0. So, this is solution of the initial value problem, that is y is equal to y0 e raised to a into bracket x minus x0. So, observe that this is general solution because it contains the arbitrary constant c, and if we have given the initial values when x is equal to x0, y takes the value y0, we get the particular solution of this differential equation. Now consider one more problem. Find the general solution of xy dash plus 1 plus x cot x y is equal to 0, and hence solve the initial value problem xy dash plus 1 plus x cot x y is equal to 0, given that y of pi by 2 is equal to 2. So, consider the solution. The given equation is xy dash plus 1 plus x cot x y equal to 0, or dividing by x, we get y dash plus 1 upon x plus cot x into y is equal to 0. That is dy by dx is equal to minus 1 upon x plus cot x y, or dy upon y is equal to minus 1 upon x plus cot x dx. Now see, this is variable separable form because y terms are on LHS on one side and x terms are together on another side. So, this is variable separable form. Once we get variable separable form, integrate that. So, integrating we get integral dy upon y is equal to minus integral 1 upon x plus cot x dx. Integrating we get ln of mod y is equal to minus ln of mod x plus ln of mod sin x plus some constant of integration k, or we have ln of mod y is equal to minus mod x into mod of sin x plus k. We are able to write down simply as y is equal to minus x sin x. See, this becomes e raised to k. So, we are able to write down this as mod y into mod x sin x is equal to e raised to k, or we can write down mod y is equal to e raised to k upon mod x sin x, or simply we get y is equal to c upon x sin x, where c takes the values e raised to k when y is greater than 0 and minus e raised to k when y is less than 0. So, this c is nothing but constant. So, we get the solution y is equal to c upon sin x. Observe that this is general solution as it contains the arbitrary constant c. To get the particular solution, we will solve this initial value problem. It is given that when x is equal to, initially when x is equal to pi by 2, then y takes the value 2. So, we substitute this in this equation 1, substituting x is equal to pi by 2 and y is equal to 2, we get 2 is equal to c upon x is pi by 2 into sin pi by 2. We know that sin pi by 2 is 1 and therefore, we get 2c upon pi is equal to 2 or c is equal to pi. Once we get the value of c, we substitute that value in equation 1, we get y is equal to pi upon x sin x. This is nothing but solution of this initial value problem, that is y is equal to pi upon x sin x. So, once we get the general solution, substituting the initial values, we are able to find the value of c and that gives the solution of initial value problem. Observe that both these examples are some special cases of one of the theorem. So, we are going to see the theorem. It says that if P is continuous on open interval AB, then the general solution of linear first order homogeneous differential equation y dash plus pxy equal to 0 is y is equal to c e raised to minus integral px dx, or we will say that the solution is y is equal to c e raised to minus capital Px, where this Px, capital Px is nothing but integration of small px dx, which is anti-derivative of this small px dx. So, we want to prove this theorem that if P is continuous on open interval AB, then the general solution of this differential equation is y is equal to c e raised to minus integral px dx. See why. So, consider firstly first part, that is we have given that y is equal to c e raised to minus integral px dx. Differentiate this y. So, differentiating with respect to x, we get y dash is equal to minus c, derivative of e raised to integral is minus integral px dx, and into px. We have taken this minus sign firstly. So, see that y dash is equal to minus c, derivative of e raised to x is e raised to x, and derivative of this becomes minus px. So y dash is equal to this. But what is c e raised to minus integral px dx? It is nothing but y dash. So we get y dash is equal to minus this c, and e raised to integral px dx is nothing but y. So we get minus pxy. By substituting these two in this equation, we get y dash is equal to minus pxy, that is y dash plus pxy is equal to 0. Observe that y satisfies this differential equation, therefore y is solution of this differential equation. Because y satisfies this differential equation, this means that y is solution of this differential equation. So in the first part we have shown that y is solution of this differential equation as it satisfies it. Now we will prove that every solution of this differential equation is always of this form. So we want to show that every solution of equation 1, every solution of equation 1 is of the form given by 2. So if you take c is equal to 0 in this equation, y is equal to c e raised to minus integral px. If you put c is equal to 0 in 2, then we have y is equal to 0, which is nothing but trivial solution. So setting c is equal to 0, we get the trivial solution of this equation. So assume that y is any non-trivial solution of equation 1. So we have y dash plus pxy is equal to 0. That is dy by dx is equal to minus pxy, or dy upon y is equal to minus px dx. Observe that this is variable separable form. Once we get variable separable form, we integrate this. So integral dy upon y is equal to minus integral px dx, or ln of mod y is equal to minus integral px dx plus some constant of integration k. So mod y is equal to e raised to minus integral px dx plus k, or y is equal to e raised to k into e raised to minus integral px dx. We take this as a c, e raised to k is some constant, suppose c, so c e raised to minus integral px dx. So the non-trivial solution is of the form y is equal to c e raised to minus integral px dx. As setting c is equal to 0, we get trivial solution, and this is non-trivial solution. Every solution of this differential equation 1 is always of the form y is equal to c e raised to minus integral px dx. So we have shown that given differential equation which is homogeneous, y dash plus pxy is equal to 0, then solution of this equation is always y is equal to c e raised to minus integral px dx, where c is arbitrary constant. So we have seen special examples of this where we have obtained the variable separable form, and integrating that variable separable form we get the general solution. So what we have studied today, we have seen what is meant by linear differential equation of first order which is of the form y dash plus pxy is equal to fx. We have seen homogeneous equation. If fx is equal to 0, that equation become homogeneous. And once we have homogeneous equation, some equations can be expressed as of the form as variable separable, and variable separable forms after integration gives us solution of the differential equation. So, whenever the equation is homogeneous, to solve such homogeneous equation, we have studied the method known as separation of variables method. Thank you.